Hi, I'm Juan-Andres, the Curator of Physics at the Science Museum in London, and today I'm going to show you the part of the Cockcroft-Walton accelerator that we have. So particle accelerators in general have existed since the end of the 19th century. First, we used them to just throw atoms at other atoms, and that helped us realize that they had a nucleus. But by the 1930s, people were wondering if the nucleus itself was made of smaller things and if one could break them up. Cockcroft-Walton accelerators were the first devices successfully used to break up atoms. And for this achievement, its designers, John Cockcroft and Ernest Walton, won a Nobel Prize. So the basic design of accelerators in the first half of the century doesn't change much. You have a source of the particles and a target, and a voltage that accelerates the particles to the target. The real difficulty is to create the voltage necessary so that the particles achieve enough of a speed to do interesting things to the target. Until the end of the 1920s, the only way to achieve such high voltages was to tap into the power of lightning. In 1927, 3 German scientists had even made a large installation in the Alps to try to use the voltage generated by touching the clouds. It was successful, but one of them died. So scientists around the world knew that the key to new discoveries was to be able to achieve such high voltages in a safe, easy way in a lab. So the most familiar name today is Robert van de Graaf. His take was a machine that was basically a modern version of what had been the electrostatic machines of several centuries ago. In these, materials are mechanically rubbed together to brush off the electrons, and then they're transported to be stored in a capacitor somewhere else. However, this is a rather brute force approach. It is successful and went on to become a more popular machine, but actually before Van de Graaf generators were used for these purposes, it was the Cockcroft-Walton machines that achieved important scientific results. So while Van de Graaf's approach in America was more of an engineer's seeking higher voltages for its own sake, across the ocean in Britain, Ernest Rutherford, who had discovered the atomic nucleus decades before, and John Cockcroft had a very specific question in mind. They knew from the theorists that with voltages of perhaps 1,000,000 volts, you could manage to bring particles into an atomic nucleus and then produce very interesting effects. Their approach was not to try to create a very expensive new device, but rather to cleverly apply a circuit design that achieved higher voltages with existing components. The first device that Cockcroft and Walton made using this design led to what was then called the first splitting of the atom. They threw protons at a lithium target and achieved in converting some of it into helium. This was the first time that a transmutation of elements was achieved using an artificial machine. So whereas in Van de Graaf generators you have single columns, you can identify the Cockcroft-Walton by having 2 parallel ones. So at different intervals up the column are the capacitors. These are the parts that store electricity. Between them are insulators, so the electricity cannot pass from one to the next. Connecting capacitors across from one column to another are rectifiers. These are like valves. They allow electricity to flow in only one direction, in this case upwards. So what this design achieves is what's called a multiplier. So for a given voltage, it can produce several times that same voltage. So the trick is that if you have alternating current, like the one we use at home, it is switching back and forth from negative to positive. What the Cockcroft-Walton generator achieves is to turn this back and forth movement into electricity that is moving actually in only one direction. So it's turning alternating current into what will become a direct, very high voltage. Each of these steps, the electrons will be at a higher voltage than before, so that as you move up the column, you reach higher and higher voltages. Eventually, you reach the large storage capacitor at the top. It is this top part of the Cockcroft-Walton generator where the particles are thrown towards a target. You can actually see at the top a hole that shows where the rest of the system would be connected to. So in the liquid analogy, if you have a water tower, the higher the water is up a tower, the stronger the pressure is at the bottom. So essentially what you're doing here is to push water higher and higher and higher up a column to create a very high pressure. In the Van de Graaff approach, you're actually trying to push water up a column directly. Whereas in the Cockcroft-Walton approach, what you're using is a bit zigzagging back and forth units of water so that at each specific point you don't need to apply a lot of force to move it upwards a bit more. But what you do is stepwise, you still achieve moving it higher and higher. So one of the novelties that made the Cockcroft-Walton approach feasible were new kinds of rectifiers. So rectifiers had long existed since the 19th century, but they were based on vacuum tubes. So if you look up close at this rectifier, it's a selenium rectifier. So selenium is a semiconductor, and so unlike the vacuum tubes of the early 20th century, this device doesn't need to be heated and it's not as wasteful. It's a very efficient device. At the end of the 1950s, physicists were using instead the circular accelerators of the kind that we still use today, and were achieving energies equivalent to 1,000 times what these had been doing in the 1930s. However, Cockcroft-Walton generators continued to be used as a feed for the new circular ones, and you could continue to see them in operation up until the end of the century because they were so robust and dependable. The discoveries made with the Cockcroft-Walton accelerator showed to physicists that the future was in research done in labs, and what you needed to do is invest more and more resources into ever more powerful devices. First, by making these into circular accelerators and making them bigger and bigger, eventually leading to massive experiments like the Large Hadron Collider, which is 5 miles across. So in a way, what we have here is the Model T of nuclear research. It was not the first one, it was not the prototype, but the one that was made serially and massively and went to labs around the world for the next 20 years. Much of the research that led to knowing how the nucleus behaves in all the elements that exist was made with very similar devices. And by the end of the 1950s, an entire new theory of how the nucleus works had been achieved, thanks to these devices. Thanks for watching. If you like what you've seen, why not subscribe to our YouTube channel?